Hello, this is Silas Gross, and welcome to Lab 6. This time it's all about flux. The purpose of Lab 6 is to observe the interaction between a metal tube and a magnet that is falling inside of it. Some of the key terms are going to be Faraday's law, it's going to be the B field from a bar magnet, and it's going to be Maxwell's equations. The preview is going to be due to the principles in a bar magnet. In a metal bar, it will stop accelerating. The first equation is the B field, caused by a permanent magnetic dipole. And the second equation is Faraday's law, where change in flux causes an electric field to form. Lastly, there's a derivation used to calculate the changing flux, and that's what's shown here. Here's going to be a visual for the principles and some of our assumptions. When the magnet enters the tube, eddy currents form above and below the bar. The top attracts the magnet, while the bottom repels it, and this creates a net F magnetic force upwards, whilst gravity points downwards. Assumptions. There's only magnetic and gravitational forces. We're not looking for force of drag here. And then there's going to be magnetic forces that are equal to gravity. So we're just saying that the top is going to equal the bottom. Experimental procedure. Oh, sorry, this is for the wrong lab. Systems and surroundings. The system is the bar magnet, and surroundings are the metal tube and the earth. The initial conditions are going to be the length of the tube, the inner radius, the tube thickness, the mass of the magnet, and the magnetic dipole moment. The experiment is going to be to drop the magnet after finding its north pole. You can try and drop it with zero velocity, which means drop it as close to being inside of the bar as you can, and then you're going to measure the time it takes to exit the tube. Here's the code. These two sections here are all about the implementation of this bottom equation, and then this one is just going to be finding the net force, and it's going to update the velocity and the positions according to that net force. And the results show that after it enters the tube, it has zero velocity, and then after it exits the tube, it regains some velocity. The similarities, differences, and possible errors is going to be that the experiment and the code show a constant velocity within the tube, and a decrease in speed when the magnet first enters the tube. However, the time it takes the magnet in the code is more than IRL. IRL was 1.15 seconds, while the time in the code was 1.19 seconds. Not a very large difference, but a difference nonetheless. And sources of error. This could be from errors when we were timing it. It was very hard to tell exactly when the magnet was dropped, since we wanted it deep inside the tube. And then it was also, we didn't want it to be too much in the tube, to where it was a shorter length than what we measured. And then it also could have been error when dropping the magnet. We could have had some sort of downward force on it that gave it some form of acceleration at the start. It could have been some coding errors as well. Maybe we didn't have a precise enough measurement. It could have been something to do with drag, where it's acting against the velocity that is going downwards. And then it could have also just been some more measurement errors, like the weight of the magnet. The what if questions. What if the resistance in the metal was zero? If the resistance in the metal was zero, then the current would vastly increase. Therefore, the magnetic force would increase. And this means there would be an extreme braking force that would result in either a levitating magnet or a very slow descent. Basically, all it's saying is that if the resistance was zero, these eddy currents would be a lot stronger, and therefore the braking force, the initial force that opposed the velocity, would be a lot faster, a lot larger, and we would approach zero velocity a lot faster. And then if there are holes that are cut in the path that the eddy current takes, if there are holes that were cut in the tube, then the path that the eddy current takes would be interrupted and would therefore be weaker. This is because the tube is treated as a huge stack of rings, so the holes would break some of those rings and would make them be incomplete paths. Thank you for your time.